This presentation is about loop vectorization. There's been previous talks about loop vectorization in previous editions of the Dev conference. There has been talks about VPlan, its integration, status updates. There have been talks about vectorization for a specific backend or different patterns. So the question is, why do we need another talk on the loop vectorizer? Well, we want to take a slightly different approach. We basically want to know how good it is. The official title is a quantitative approach to find and identify loop opportunities. So that's what this talk is about. And this is work that I'm doing with my colleagues Madhur and Sebastian, who are also attending and in the audience. So first, why are we doing this? Our motivation. Our target is an AArch64 CPU, and it has a new SIMD extension, SVE-2, which is short for Scalable Vector Extension. It is not really important, so I won't go into details here, because most of our findings and conclusions are mostly target agnostics and very generic. So the only thing that is kind of important here, that for this machine, it's a big CPU, that efficient utilization of the machine, for efficient utilization, SIMD code generation is important. So that led us to the question, okay, how well is the loop vectorizer performing? Now, to answer that question, we took two benchmarks and tried to quantify this and come up with an answer. We took TSVC-2 and RAJAPerf, two benchmarks. And what we did is we benchmarked these two benchmarks with different compilers and different options, like different optimization levels, so O3, O-fast, and disabling vectorizers. And in this way, we were finding outliers, and we were finding opportunities and regressions. So the next step is then, okay, then we want to identify the root causes and create a plan for addressing this. So that's what this talk and work is about. I mentioned two benchmarks. In this presentation, I will be only talking about TSVC in the interest of time. And TSVC is short for Test Suite for Vectorizing Compilers. It's part of the LLVM Test Suite. So if you run the LLVM Test Suite, then you'll be running TSVC. It's basically one file with 152 small functions, kernels, so it's kind of loop-based functions, and they try to stress test different patterns that a vectorizer could handle. So this is kind of the problem statement. We took TSVC and run this and compared this, and this is a comparison with GCC13, and this was at the time a recent LLVM trunk version. So what you see here on the left-hand side, these are all the cases here where GCC is faster. So here you have cases where GCC is 2x faster, 3x faster, 4x, and there's one that is off the scale faster. We have cases that are similar, same or similar performance. Different things could be going on here. They could both GCC and Clang could vectorize it, or they could both be scalar, or one could be scalar and vector. Could potentially be interesting cases, but we have not looked at that. And here we have cases where Clang is faster. Now, we were interested in making improvements, so we only focused on kind of the left-hand side here. So these regressions. We classified them as the interesting cases. So with this data, we then created a kind of a short list, a list of outliers, top outliers. So this again is Clang versus GCC13. So we took all the cases that were at least 1.5 times worse with Clang. And if we look at this, the top outlier is a 16x regression. And the reason is that Clang is not doing loop interchange, which can enable vectorization. This is available in GCC, and it's not in Clang, which results in a 16x regression. GCC knows another trick. It can do out-of-loop vectorization, and that results in a 4x regression. There is kind of inefficient code generation, vector code generation for control flow, and that results in a 3x regression. We're not interleaving enough, so interleaving is essentially unrolling of the vector body. We are not doing that. Sometimes SLP vectorization is more profitable, so we have a case where The SLP vectoriser was not performing well enough, and that was a 2.5x regression. Loop peeling, kind of another enabling optimization. We are not doing that. GCC is doing that a little bit better. Then, maybe surprisingly, found also some scale optimizations. Some test cases are not really meant for vectorization. So here you see, where's my cursor? Here we see predictive commoning. That is also an that's also an optimization in GCC, and we're missing that. Then we have some kind of basic cogen, unnecessary sign extensions getting in the way of things. Again, we have a case of outer-loop vectorization, which is good for 2x regression, the SLP vectorizer, and all sorts of issues related to cost model where we should vectorize or we shouldn't, and that results in 1.5x regressions. So that was our list. If we try to cluster this a little bit, then we see a class of problems related to loop optimizations. So we're not interchanging. We are not doing out-of-loop vectorization. One way to achieve that would be enabling on-row and gem followed by SLP vectorization. We're not doing that. Loop peeling needed to be taught a few tricks. The loop vectorizer itself, that's mainly tuning in terms of more interleaving and epilogue vectorization. Epilogue vectorization is available in Clang. It's effectively disabled because of a very high threshold, which is being addressed by Apple. And then all sorts of cost modeling issues. Cost modeling, whereas for some cases we shouldn't vectorize because it's not profitable, or we have also the possibility to go fixed width or scalable vectorization, all these kind of decision making. And then maybe surprisingly, we also found some scalar optimizations like predictive commoning. Now, comparing with another compiler is easy to do. It does not tell us what the best thing is that we can do. So we then did a manual exercise where we basically looked at source code and made manual modifications to the source code. And in this exercise, we restricted ourselves to 2 loop optimizations, loop distribute and interchange. And we tried to modify the source code and see what the best thing that we could do. Now, we found that we can vectorize more. So in this table here, the bold cases are things that we could now vectorize, which we couldn't vectorize before. And the other cases see higher gains. So the first row is if we enable loop distribute, we can get a nearly 36x improvement. For some cases, when we combine loop distribute and interchange, we get a 22x improvement, and so on. And the two bottom rows, when we combine loop distribute and interchange, we can enable more vectorization for different cases. They were manual exercises, but there's really no reason why this could not be done by the compiler and with the transformations. So this is basically saying that we leave a lot of performance on the table. And really a lot. We already did some work. So this is kind of our work that we did during the summer. So when we started, there were 37 cases where Clang was worse. We started working on this, and after some of our patches landed, we brought that down to 26, and finally to 24. The number of cases where Clang was better was going up from 90 to 24. I think here is just a blip in the buckets. And the number of cases where the performance is same, it was going up from 96 to 102 and 106. So all these signs showing that we are making improvements. These improvements basically fall into kind of 2 buckets. The improvements that we made here resulted in 2x improvements. And they were the improvements related to cost modeling, heuristics, and cogen. And what we want to do next is kind of to enable the performance improvements that will go beyond 2x improvements. Now, I wanted to give you a quick impression of the kind of things that would give us 2x improvements. There is a lot of kind of tuning that can be done in subtarget.cpp. There's all kinds of parameters that can be tuned. The first one that I mentioned is max interleave factor, and which controls the unrolling of the vector body. Unrolling that could result in better utilization of the SIMD pipes. The default is low, it's 2, but kind of a good rule of thumb is that the default should be equal to the number of vector pipes that you have. So that's something that we increased. And again, I'm just showing you, because this is something that you could easily check for your target. There's kind of another threshold to control the generation of scatter instructions. We tuned that so that actually for some of the cases they would not be generated because that's faster. Some changes to the loop vectorizer. To be a bit more specific, the cost model. The way the cost model works is that it evaluates different alternatives for different vectorization factors. It assigns a cost and then it picks the lowest one. The question is, what do you do if there are variants with the same performance? So we introduced this hook where you can then steer if the cost model is undecided what to do, and that resulted in a very big improvements for us. If you interleave more, then the next thing that becomes really important is epilogue vectorization. Because if the iteration count of the loop is low, it could be the case that you will not enter the vector body anymore, but just the epilogue loop. And in that case, vectorization of the tail, the epilogue is important. So we did some work there to enable that. We did some work for loop peeling so that will then also trigger more vectorization. And as I mentioned, we have all sorts of different patches in the cost model that then allows more vectorization. During this exercise, we identified 3 problems. This is the first one. I'll talk about the others in a minute. I already mentioned that we had a lot of cost modeling patches, and it's kind of the first problem that we identified, the cost model. The way it works is by basically recognizing IR snippets and assigning a cost to it. Most of the patterns are handwritten, and it's not really expanded to a low-level IR, so you don't know really what you're cost modeling. But then the other problem is that we're doing this on IR, and it means we're not looking at any of the information that is available in the backend, like latencies, throughput, and resource descriptions. We don't have access to that. Now, the issue with this is, because these are mostly hand-written patterns, there's always a case missing. So for new CPUs or tuning, it is kind of an endless tuning exercise. And it's lacking quite some precision because it works on IR. Now, for the other problems that we identified, we will have ROCs. This is more like what is bothering us, so I don't have a concrete ROC yet. But in an ideal world, what we have instead is kind of a set of test cases where we map IR snippets to cogen. And for this cogen, we can extract metrics, for example, with MCA. And then we can populate a cost table, a database. The benefit of that is that you can then update it if the cogen changes, or for a new CPU, you just generate that. That's kind of the idea that we would maybe in the future like to explore. So now moving on to beyond 2x improvements, what do we need to do? We kind of fixed the basic cogen issues. What's next? Well, as I already mentioned in the beginning, that's probably loop optimizations, and there are quite a few of them. So in LLVM, there's interchange, unroll, and jam, distribute, and fusion. And from this list, we will mainly focus on interchange. And I will go into details, but loop interchange, because it's kind of a general transformation, it's good for data cache improvements, and it enables vectorizations if dependencies get in the way. And perhaps unroll and jam too, as I already mentioned. Because it can achieve out-of-loop vectorization if it's combined with SLP vectorization. So that makes that a very interesting transformation. Now, next problem is loop optimization. So all these, as I mentioned, all these loop optimizations are available. The problem is they're all off by default. So all of them, unroll and jam, interchange, fusion, distribute, they're all off. So the question is, why are they all off? Can't we do this in LLVM? Well, there is an element to that because for the legality of these loop transformations, we need to do data dependence analysis. And that means that we are interested in finding the access patterns to the arrays. So in case if they are multi-dimensional arrays, we would like to recover these multi-dimensional array access. Problem is that most of this information is gone, it's flattened, so we need to recover this information, which is what the delinearization is doing. That is made more difficult because of IR simplifications. So that is making that more difficult. But we think it is okay enough to recognize and enable quite a few cases. Now, the other question you may have, okay, this is all disabled by default. Is it not important? Is this only fun for benchmarks, but not for real-life code? Well, that's something that we can measure. And that is the reason why we would like to start with enabling loop interchange, because it's very generic. This is just a snippet from the LLVM test suite where it triggers in a lot of cases. Of course, the question is, what are the performance improvements? I will get back to that in a second. But loop interchange, because it's relatively simple and straightforward as a transformation, and we would like to use this to get basically a foot in the door with loop optimizations in LLVM. So what we need to do is we are aware of the problems raised against both components. So what we want to do is fix the problems in interchange, in dependence analysis, and collect compile time numbers and see if we can get loop interchange enabled. Just before this dev conference, we started a RFC about that. Now, the last problem that we have is evaluating all of this. So vectorization, we make changes. How do we know if it's better or worse? So kind of the last problem that we identified is the test suite. There's kind of a famous research article that says why most published research findings are false. I would probably go as far as saying that the same is true for the LLVM test suite. If you rely on the LLVM test suite for vectorization, you are probably making the wrong decisions. The reason is, in the case of TSVC, all kernels are in the same function. If you make changes to one function, that may influence the behavior of a function that is unchanged. And that's because of code layout issues, that kind of things. So there's a lot of noise. So we found basically that if there's a change of about 20–30% in a TSVC kernel, it's probably not real. It's probably noise, at least in our cases. So if you just run the test suite 1, 2, 3 times and see a 20% improvement in some TSVC kernels, it's probably not real. Other problems is the test suite is very old. I had a patch to document all the apps in the part of the multi-source benchmark. And I tried to find the original sources of it. Most of them are not available. The apps run for a very short time. I think most of them measure more I/O than anything else. So that's quite problematic for evaluating this. So what we want to do is first we want to modify TSVC, place each kernel in its own function to minimize noise. And we want to add different benchmarks. We think RAJAPerf is a good one. It's fast, small, more representative. And we also started an RFC about this. So to conclude, TSVC is an artificial benchmark. We appreciate it, but it has been extremely useful to find all sorts of generic code-gen deficiencies. So it's very easy to compare flags and optimization levels. And all the things that we found in these artificial benchmarks are all generic cases. And yeah, so I talked about the 3 problems. All loop optimizations are disabled. We're going to work on fixing dependence analysis and hopefully get loop interchange enabled, hopefully soon. The LLVM test suite is unreliable for us to measure performance. So we'd like to start working on adding more representative benchmarks to it and actually fix some of them. And the one that we have on our wish list is the cost model. We think something needs to be done about that, but that's for another time. That's it. Thank you.
How often do you see regressions when performance drops because something was vectorized which was not supposed to be vectorized?
Yes, often. And that's all the cost modeling work that you do. So you hope then to tweak it and fix that case and hoping that the rest doesn't break. Yes. Yeah, very often.
Nelson Amaral from the University of Alberta. I'm very happy to see your work at this characterization. And I'm happy that in the end you point how artificial TSVC is. Mm-hmm. But I think that everybody has to realize how really non-representative it is. Mm-hmm. It was created by David Callahan 36 years ago as a collection of 100 loops from Fortran. And the idea was that they should be different and difficult to vectorize. This is not what you want from the benchmark, right? You want it to be representative. TSVC is not representative of anything but that snapshot from 1988 of loops that were very different from each other.
I fully agree. But the thing is, all the things that we fix, we verified this also that we are doing the right things with other benchmarks. But
there's this point, when you're measuring something, is what is it that you're measuring? Is it representative? That's the point that I want to make.
Yeah, sure, fair enough.
So on the point of disabled loop optimizations, I imagine they're disabled because of they cause correctness issues. So if we just re-enable them, have you found any correctness issues with more extensive testing?
So for loop interchange, for example, we are aware of 4 problems. There in the GitHub issues, there are about 4 or 5 issues raised against loop interchange. 2 of them are simple asserts. 1 is slightly more serious. So that's kind of the order of bugs that you think about. And that's not unusual. And I also think that a lot of at least some of these loop optimizations are enabled in downstream compilers. And what I want to say is they are used. So I think there's quite some interest. I think on the RFC, I think it shows that there's quite some interest in getting this enabled. Really the main thing is dependence analysis. That is fragile.
Hi. Quick question. Have you considered gathering this data from spec too?
Yes. But spec is, yes. There's one benchmark that is good for vectorization, X264. The rest not so much. From spec FP, the Fortran benchmarks are really interesting for vectorization because they're very suitable for vectorization. So I don't have the data, but yes, we look at that.
Good work. You mentioned that you did loop interchange for vectorization. Did you also do loop unrolling? Was there any for vectorization?
I think I was going to say loop unrolling is kind of part of the vectorization strategy.
Okay.
I mentioned, interleaving, which is some sort of unrolling. And that's, in our case, we just wanted to crank up the heuristics a little bit. So, yes. Yeah.
Thank you for your talk. I have one question. So you mentioned like the most of transformation was done manually. Have you considered any sort of like Clang MLIR front end, like Clang IR or like Polygist, to like do maybe some of these like loop transformation at MLIR level and then lowering it to LLVM, and then maybe LLVM like vectorization can kick in?
A very good question. Yes, we talk about this quite a lot. Yes, it's very interesting because some of the abstractions hopefully make some of these transformations more easy. The question is cost modeling, I think. So when you talk about vectorization, you also have to start talking about cost modeling. And I don't think that is available in MLIR. So you have to kind of raise all of these analysis to the MLIR level too, I think. But it's a good point. Yeah.
Again, thanks for the talk. I just have two questions. What
Yeah.
optimization level did you use? Was it O2 or
Sorry, this
O3?
was O-fast. Yes.
O-fast?
Yeah.
And when you talk about your examples for loop distribution, you said you you distributed by hand. If I
Yes.
understood this right.
Yes.
But since we have loop distribution in LLVM, how would it compare if you turned it on?
I don't know is the answer, but
Okay.
that's on our list too. We our short list is interchange, unroll and jam, because it's one way to achieve outer loop vectorization without implementing that in the loop vectorizer. And yes, distribute is high on our list. Yeah. Yeah.
I think, was it Preston who was working on dependence analysis like over a decade ago? And I don't believe it was ever used for anything because of some problems. Do you know what those problems are? And do you have an idea of how to fix them? And also, I suppose it's going back to the previous question before, is it really the right thing to use for these kind of things? Or do you think there might be something else we can use to get you that information?
Yeah, so the problem with dependence analysis, let's say it's not broken, not fundamentally broken. So we are in the process of improving it. Again, I think there are about 2 or 3 issues raised against dependence analysis. One of them is can result in miscompletions. And Sebastian in the audience is fixing that. So it's not, it's there and it's stable. It's fragile because we try to recover this type information, the array access. So fragile in the sense not that it's miscompiling, but it's missing cases. So what we'd like to do maybe, that's something we are thinking of, is trying to, maybe with some metadata or instrumentation, is to propagate some of the type information to IR so that we don't need to recover it. That's our current thinking.
Okay, I think we already ran out of time. I think loop vectorization is a very popular topic. Yeah, if you have any questions, you can talk with Meijer offline. Thank you. We will start our next presentation in 3 minutes. Thank you.